Hello, we are continuing on with determining the probability of two or more events today, focusing specifically on independent versus dependent events. So if you remember from last time, and it has been a while now, we looked at dealing with mutually exclusive versus non-mutually exclusive events, and the connecting word we were focusing on to help us identify that was the word or. So in terms of independent versus dependent, the connection word that we're going to take a look at is the word and. What is the probability of this and this occurring? And there's two different types of events that are going to occur. The first one is independent events, dependent person. They are a person who is not generally impacted by outside events. It's similar with probability. So the probability of one event occurring has no impact on the second event occurring. For example, if you were to roll a dice, the number that you get when you roll the dice has no impact on whether or not you get heads or tails when you flip a coin. So those two events are what we call independent events. In terms of the notation, going back to set theory, the probability of event A and event B occurring, we're going to determine the probability of event A. Remember, and in mathematics generally means multiplication. We're going to multiply that by the probability of event B occurring. The second type of probability, using the word and, is dependent probability, which is also called conditional probability. So with dependent probability, what happens in the first event does have an impact on what happens in the second event. So for example, if we think about a deck of cards, if we draw a card from a deck and don't put it back, that then impacts the probability of drawing a second card because we no longer have 52 cards in the deck. So if I was to determine the probability, let's set this up here, of drawing a heart and a heart, I'm going to begin with the denominator. So there's 52 cards in the deck, and a quarter of the deck are hearts. So there are 13 hearts in a deck. We're going to multiply that. Now, the keyword here is we are not replacing the cards. So if I pull a card out and don't put it back, there are now 51 cards in the deck. And if I took out a heart, I now have only 12 hearts in a deck. So I'm going to multiply. When I'm multiplying fractions, I'm going to multiply the numerators. 13 times 12 gives me 156. Multiply the denominators. 52 times 51 gives me 2,652. You can reduce that down to 1/17th. You can turn it also into a decimal or a percentage, depending on the format that they ask for. If they don't specify, any of those three are fine. So in terms of the notation now, we can say the probability of event A, remember and, that's our little slap chop, B, we're going to find the probability of event A, and we're going to multiply it by the probability of event B given that A has already occurred. Now, this is the one thing that is a little bit different than set theory notation. In set theory, the second term says B but not A. Because we're dealing with probability now, we actually say what is the probability of B, and then given that A has already occurred. That's the one notation that's different from set theory to probability. Look at a few examples here. So a question that sometimes comes up is determine whether or not two events are independent or not independent. So this particular example, number one, is using the set theory notation. So we're going to take a look at this and we're going to say, okay, what is the probability of X and Y occurring? So we know there's our slap chop, there's and. So we're going to say, okay, we're trying to determine, are these independent or not? And then go back to what we know about independent events. We know events are independent if we can take both probabilities and multiply them together. So that's what we're going to check. We're going to say, okay, if we take the probability of the first event, 0.52, and multiply it by the probability of the second event, 0.13, will we get 0.68? And when we multiply them, we actually get 0.0676. So clearly, 6% is nowhere near 68%. Therefore, because they don't multiply to that 0.68, we know that they are not independent events. They're going to therefore be dependent. Okay, so this does not equal that. So they're not going to be independent. The second one is a word problem. Determine the probability that a face card is drawn from one deck and a spade is drawn from a different deck. So we have two decks of cards here. So because we have two different cards, and again, there's our keyword, so and, we're going to say, okay, what is the probability of drawing a face card and what is the probability of drawing a spade? So in the first deck, there are 52 cards. And the jack, the queen, the king are the face cards. 3 face cards per suit. 4 suits means there are 12 face cards. And we're going to multiply. Now, this is a different deck. So we still start with 52 cards. And we know that in a deck of cards, 13 of them are a spade, or 13 of them are one suit. So we multiply the numerators. And 12 times 13 gives us 156. 52 times 52 gives us 2,704. And again, we can reduce that if we want to 3 over 52. We could turn it to a decimal, or we can turn it to a percentage, whichever your heart desires. So that's different from the example up above that we did previously. So in this particular one up here, right here, we did not put back the one card. That changed the denominator on the second one. These are dependent. These ones down here are independent. Look at some different types of examples you might see. Number 4 is a fun one. So we have 2 dice. One is red and one is blue. And remember, when you're talking about dice, you want to picture different colors. When you're talking about coins, you want to picture different denominations. So we're rolling them at the same time. Is what we roll on one dice going to have an impact on what we roll on the second dice? Keep that in the back of your head as we work through these. So the first one wants to know, what is the probability of rolling a red even and a blue odd? Okay, so let's think about this. So I'm going to take my red pen here, and we're going to say, okay, what is the probability of rolling a red even? So on a dice, regular 6-sided dice, the options of an even number are the probability of getting a 2, a 4, or a 6. And I'm going to use my ampersand. What is the probability of rolling a blue odd? So on the blue dice, we have an option of 1, 3, 5. So start again with the denominator. So there are 6 choices on a dice, and 3 of them fit the criteria we're looking for, and we know means multiplication. On the second dice, again, there are 6 options, 3 of which fit the criteria that we are looking for. Multiply the numerators. 3 times 3 is 9. Multiply the denominator. 6 times 6 is 36. And that will reduce to 1/4, which you can also turn into 0.25 or 25%. So we have 1/4 or 25% chance of that scenario occurring. Okay, so now, what is the probability of rolling a red prime number and a blue number that is not greater than 4? So again, we're going to set this up. So the probability, so now think, what are your prime numbers? Not 1, remember. So we have a choice of 2 is a prime number, 3 is a prime number, and 5 is a prime number on a 6-sided dice. And we know is multiplication. And then, I'll go like this, and then what is the probability of rolling a number not greater than 4? So if it's not greater than 4, our options are a 1, 2, 3, and we can have 4. We just can't be greater than 4. So again, let's set this up. There are 6 choices on a dice, 3 of which fit our criteria, and we know means multiplication. Second one, there are 6 choices on a dice that fit the criteria, 6 sides on a dice, 4 of which fit our criteria. Multiply the numerators. 3 times 4 is 12. 6 times 6 is 36. And this will reduce to 1/3. Okay, that brings us to C. And notice what's different about C than the previous two, A and B. Well, A and B specified the red dice does this, the blue dice does this. C doesn't. So we have to account for both situations. So it says one dice rolls a multiple of 3. So we're going to start with, okay, let's say the red dice rolls a multiple of 3. Well, on a dice, the multiples of 3 are either 3 or 6. The other dice rolls a number that is not a multiple of 5. So, well, the one dice is doing that. The next dice is going to roll a number not a multiple of 5. Well, the only multiple of 5 on a dice is 5. So everything else fits under 1, 2, 3, 4, 6. That's one scenario. Or the second thing that can happen is we can have the red dice rolling a number that is not a multiple of 5. 1, 2, 3, 4, 6. And we can have the blue dice rolling a multiple of 3. 3, 6. Okay, so I'm going to fill in my operations first. So we know OR is addition. We know AND is multiplication. So we have 2 scenarios that could occur. There are 6 sides on a dice. So I'm going to start with the denominator, 2 of which fit the criteria there. And I'm going to do the red dice over here just to save time. 6 sides on a dice, 5 of which fit the criteria. And 5 fit the criteria here out of 6. And 2 fit the criteria here. When we multiply fractions, we multiply the denominators and the numerators. And then again, denominators and numerators. When we add fractions, we need a common denominator, which we have. That denominator stays the same. 10 plus 10 is 20. And again, you can reduce this to 5/9. The probability doubles because there's 2 situations we have to account for. It doesn't specify which is which. Letter D, we have 2 dice, and the sum of those dice is 7. We can do this the way we did it previously, where we set up a chart that contains the sample space, and then out of the 36 outcomes, we can just look and see 6 of them, or 1/6 of them, contain a 7. So you have a strategy already for how to approach a question like that. So that's one way you can go with. The second thing you can do is you can say, okay, on a dice, I can get any one of those 6 numbers to roll, and then one number is going to add to that to make a 7. So I can get the probability, I can have any number on the first dice. So out of the 6 sides, or 6 numbers, all 6 of them could potentially add to 7. And on the second dice, I need one number to match. I'll put that. So basically, if I roll a 4 on the first dice, what do I need to get on the second dice to get to 7? I need a 3. If I roll a 5 on the first dice, I need a 2 to add to 7. So out of these 6 sides, there's only one that's going to match. So 6 times 6 is, 6 times 6 is 36. 6 times 1 is 6. And again, that reduces to 1/6. So someone had made a comment last week when we were looking at the sample space. They said, well, that is technically 2 events, and you're right. These are dependent events. So if we're going to add to 7, the second number that we get depends on what has already been rolled on the first one. Probability is used to determine the likelihood of an individual having a disease or not. No test is ever perfect. If somebody, either a human or animal, is healthy, they're most likely going to test negative for a disease. So we can figure out by multiplying them, what's the probability that an individual is healthy and tests negative? It's going to be fairly high. However, because no test is ever perfect, The test can come back negative, indicating that the person or animal does not have the disease, but there is a small likelihood that they are actually sick. So we can calculate that probability too. What's the probability that they are sick but came back with a negative test? And then likewise, the same thing works for a positive test. If you are sick, there's a high probability you're going to test positive. What's that result? But there is also a small chance of the reverse happening here. So this is one example pertinent today of how probabilities can be used in varying situations. And this is a tree diagram set up, the number 5. Feel free if you want to try that one on your own, go for it. But we're going to take a look at the last one, similar to how to set it up using a tree diagram like we just looked at. So in this particular case, we have a soccer team, and it gives us varying probabilities for their chances of winning in different circumstances. We are ultimately looking for what is the probability that this team is going to win tomorrow. And there's 2 different conditions in which they can win. So they can either win when it's windy, or they can win when it's calm. So I'm going to set this up here. Win when it is windy and win when it is calm. And then I'm going to go through the question and try to fill in my numbers. So tomorrow I have a 40% chance of high winds. So then if I go over here and say, okay, so tomorrow there is a 40% chance of high winds, which means there is a 60% chance that it's going to be calm. These 2 numbers together have to add up to 1. I'm either going to win or lose tomorrow. And the same thing with being calm. I'm either going to win or I'm going to lose. So then we're going to go through the question and try to pull out some numbers that we can put in here. So we can see already I have a 60% chance of winning if it's calm. So I'm going to go in here and say, okay, if it's calm, I have a 60% chance of winning, which means I then have a 40% chance of losing because, again, these 2 numbers have to add up to 1. I have a 70% chance of winning if it's windy. So then I'm going to fill in here 70% chance of winning and being windy, which means I have a 30% chance that I'm going to lose when it's windy because, again, these have to add up to 1 whole. So then we can go through and multiply these. If I'm going to win when it's windy, I have windy and win. I'm going to multiply those numbers together, and there's a 0.28% chance, or 0.28 chance, 28% chance of that occurring. I have so multiply these together. So windy and lose, there is a 12% chance of that occurring, or 0.12. Continue on here. So being calm and winning, multiply those 2 together, and we get 0.36. And then finally, if I multiply calm and losing, I'm going to get 0.24. Okay, so I didn't need to do all of those, but I filled them in just so you can see what's happening. I only want the probability that the team will win tomorrow. So the 2 conditions in which we can win are windy and win. So that's this one here. Or I can win when it's calm. So that's this one there. I'm going to total those 2 together. And when we add those 2 up, we get 0.64. So I have a 64% chance I will win, or not I, the soccer team, will win tomorrow. All right, so that is the end of virtual learning day 1. We're going to try a few practice questions here. So you can grab your textbook, and I'm going to get you to try on page 189, number 9, is a conditional probability question where you can set it up similar to the tree diagram above. And then 198 gets more into differentiating between dependent and independent events. And we're going to try here. Numbers 1 to 15 odd. And you can omit numbers 3 and 11. So give that a try. And if you need help, we're going to still kind of figure out the best way to go about addressing those questions. So thank you for bearing with me, and I will see you soon. Take care. Bye. We have 51 cards in the deck. Oh, and there is a problem already. So let me grab the eraser here. There we go. Now, dependent probability, also called conditional probability, is where one event does not have an impact on the other event. So for example, or sorry, that's not true. If one event does have an impact on another event. Okay, now what's different about number 3 compared to numbers, or letter 3 compared letter C compared to letters A and B?